Okay, let's get started. All right. Okay, so last week we introduced the Wiener process or the Brownian motion. Okay, then we showed that integration with respect to the Brownian motion is not well defined under the traditional integration in calculus. Okay, so we'll show you how we define a stochastic integral with respect to Wiener process today. Okay, so the step is as follows. First, we define the integral for a set of simple process. Okay, and then we say for any process, we can approximate by a simple process. And finally, we show that such definition will lead to a well-defined definition, which means we will have a unique solution for the integration, right? So which means it both exists and it's unique, all right? Okay, recall, when we talk about stock price, we typically model the change of the stock price, okay, on the left, the change of the stock price over a time delta t to be of two components, okay? The deterministic component, which is a multiple of the duration delta t, okay? So this mu is called the drift. And then a stochastic component, okay, where we have the delta wt. But we know for different stock, they have different level of variations. So we have a scaling factor sigma, okay? Now, let's consider a partition, okay, from 0 to t, from t1, t0, t1 all the way to tk, okay? And the return for this stock from 0 to t will be the sum of all the delta s, okay? Suppose this is delta st, okay? Suppose we denote this to be delta st, then the total return from 0 to time capital T will be the sum of delta st, right? So if we substitute that, for each component will be its respective mu and the duration plus its respective sigma plus the delta wt. Okay? Right, this happens in the discrete world. And now, if we let the delta t to goes to 0, okay, the duration between any two time points to goes to 0, and this leads to the definition of the stochastic integral, okay? So from from 0 to capital T, the total change will be an integration. The first is defined in the traditional calculus, okay? So we integrate mu over the time horizon from 0 to t, okay? So this is well defined. And then the random component, okay? We integrate the sigma with respect to the Wiener process Wt, okay? All right? Or we can write the equation in a SDE form, okay? Stochastic differential equation, all right? Okay? So basically we have St minus S0 equals to okay, so this is the integral form, and then we take its derivative. Then this one is delta dst, And then for the remaining two terms, we can just remove the integration sign. Okay? But we have shown last week that a Brownian motion is nowhere differentiable. Right? So what is dWt? Right? We have shown that the variation of Wt is infinite. Okay? Okay. Let's consider a trading strategy. Okay? It's a portfolio. And it's a dynamic strategy such that at time ti, you hold HTI shares of the underlying. Okay? So since at ti you hold HTI shares, then from ti to ti plus 1, your return will be the first, for one share, your return will be STI plus 1 minus TI, right? And then since you have HTI shares, so this is your return over from TI to TI plus 1, okay? All right. So then from 0 to T, from 0 to capital T is a sum, okay? Sum of the return over each single period. And again, if we let this delta t goes to 0, then we reach to the definition of the stochastic integral again. Okay? All right. So the first part again is deterministic, okay? Which is well defined. But what is unclear is the second part. And that is our today's goal, okay? We want to find the definition of okay? A function of t. But if you look at the equation, we also have st, but st is also a function of t, right? Okay? They are both ft adapted. Okay? Okay. So we first define the Ito's integral for simple process. Okay? For simple process. What is a simple process? So a simple process, xt, has this form. Okay? So it says it starts from cosine 0. It starts from cosine 0. Okay? It starts from cosine 0, which is 0. Oh, sorry, it's not 0. It starts from cosine 0 at time t0 to t1. Okay? So it means from t0 to t1, cosine the simple process x is a constant. Okay? It's a constant over t0 to t1. And then from t1 to t2, it will be cosine 1. Okay? It will be cosine 1. And for cosine j, it is, oops, sorry. Okay. So for cosine j, it is ftj adapted. Okay? Which means this simple process is a constant for a duration. And the information is known at the beginning of this time period. Okay? The information is known at the beginning of this period. All right? Okay. So this is an illustration of a simple process. Okay? So from time 0, it starts from a constant cosine 0. And when it reaches t1, it jumps to another constant, okay, for a period of delta t. So within each period is a constant. Okay, so this is a simple process. Okay, so we define the stochastic integral or Ito's integral for a simple process if we consider in the conventional calculus, when we integrate this with respect to t, okay, respect to a variable t, so this we can define to be the sum, okay, in the discrete space is its value at the beginning. So its value is fixed in this period, right? From this is ti, this is ti plus 1, and this is psi I, right? So the integration over this period will be cosine I times delta t, right? Okay? So the last term is for the completeness, okay? It's only for the completeness because this can be your Tm, this is your Tm plus 1. And if your T is here, okay, oh, here we use small t. So if your T is here, then the last term is this integration from Tm to T, okay? So the last term is only for completeness. So we will define the integration of a simple process with respect to the Brownian motion in a very similar term. That is, the integration is respect to a Brownian motion. We just replace the variable t with the Brownian motion. Okay? So we replace dt by dwt. Okay? All right. And the reason why we can define it like this is because, remember, the simple process is a constant, okay? It's a constant within each period. Okay? And again, the second term is for completeness. Okay? It's for completeness. All right? So this is the definition for integration of simple process with respect to Brownian motion. Okay, so remember this cosine simple process is adapted to the FTJ, okay? So cosine J is adapted to FTJ, means this information, the value of cosine Tj is known at the beginning of the period from Tj to Tj plus 1. Okay? So this is important because we always remember that we cannot use any future information. Okay? So we price a derivative for an option, or, okay? We cannot use any information from the future. And secondly, this is a martingale. So the integration defined this way is a martingale. It's one of the properties we will show later. Okay? So this is an example of an integration which we define the simple process xt to be wt. Okay? So basically xt equals to wt for t within, okay, is left is sorry, okay. All right, so we define a simple process this way, and the two graphs shows different discretizations. Okay, so the first one we cut the t over t, we cut into 10 subperiods. Okay, and the second one we cut into 25. Okay, so you see this cosine is a constant over 0.1. Okay, that delta t is 0.1. Your t is 1, right? T is 1, n equals 10. So this delta t equals to 0.1. And on the right, this delta t is 0.04. Okay, so when your delta t gets smaller, the simple process you look more like will converge, or when your n gets bigger, okay, supposedly if your n goes to infinity, intuitively this simple process will converge to the Brownian motion, right? Okay. All right. Okay. So the integration, the Ito's integration defined for the simple process has some properties. The first one is linearity, right? The linearity is trivial because a multiplication of a simple process is a simple process, right? If you have xt to be a simple process, okay, then your axt will be another simple process, right? Okay, and then you will have axt plus bxt tilde, okay, equals to at plus. This is another simple process, right? So the integration defined this way has this linearity property, okay? So this is basically the same as in the conventional calculus. Second one, we say this is a martingale, right? The expectation of such integration is 0. And second one, the Ito's isometry, okay? The variance of this integration, okay, again, the variance of this one of this integration by definition will be the expectation of the square, which is, we have seen this one, the expectation of this square minus the square of the expectation, right? Right. And then if we show this, the expectation is 0, then square is 0, right? And then the variance will be equals to the expectation of the square. Okay? That's for the first equation. And you will see it's here. If we can show that this integration is a martingale, then we know the expectation of this integration is 0. Okay? So if we can prove the property B, then the first equation in the property C is proved. Okay? All right. Okay, let's see. How do we prove it's a martingale? All right. So let's denote this delta Wj to be the change of the Brownian motion over the time period from Tj to Tj plus 1. Okay? And suppose we have two time points, S and T. S and T. Okay? With S to be smaller or equal to than T. Okay? With S to be smaller or equal to than T. So in this case, we know for sure N is less or equal to M. Okay? So it will be either be like, this is N plus 1, M plus 1, and this to be S and T. This is one scenario. The other one is N plus 1, S and T. These are the two cases, right? So if you take 2 points, they may fall into the same period or different period. Okay? So we want to compute the expectation of this integration from 0 to t, okay, to t, a later time, and condition on the filtration up to S, okay, the information up to S. Okay? So when we integrate to t, by definition, this integration is the sum over cosine I times the change of the Brownian motion delta Wi. And we have an additional term for completeness. Okay? All right. So since S is smaller than T, okay? S is smaller than T. So this W, delta Wi, when Ti is greater than S, Ti greater than S, and smaller than T, okay? So we have, suppose this is W, okay? It's W. So this is S. Then for W up to S, the expectation condition on Fs, this is equals to Ws, right? And expectation of Wt minus Ws, condition on Fs, this one is 0. Right? Right? Because this is independent of Fs, right? These are the future information beyond S. So it's independent of the past information. So this is expectation of Wt minus Ws. And because it follows a normal distribution, it's mean 0, so this one is 0. Okay? All right. So we can decompose this sum within the expectation to be the sum from 0 to S and S to T. Okay? So for those from 0 to S is here. And for those from S to T, the expectation is 0. Okay? All right? So therefore, we prove it is a martingale. Okay? I think we have, yes, we have it here. So we have we discussed the two scenarios. How do we actually prove why the second part is 0? Okay? Why the second part is 0? Okay. So we consider two scenarios. There's two scenarios that I just mentioned. The first one is S and T falls in two different periods. Okay? It falls in two different periods. So then the expectation of this part is we have up to Tn, okay? Tn minus 1, sorry. So we have up to Tn minus 1, this part. They are all, the information of up to Tn minus 1 are all known at time s. So that's why we can take it out from the expectation. Okay? And for any time beyond Tn plus 1, okay? For any time beyond Tn plus 1, their expectation is 0. Okay? Their expectation is 0. So what we left is from S to Tn plus 1. Oh, sorry. Is from S to Tn. Okay? We left with S to Tn. Okay? This part. Okay? And then these two terms together is precisely the definition of the integration. All right? In the second case, if we have n is the same as m, which means S and T are in the same period. Okay? If at the same period, then we have this definition. We have the first term, okay? The first term, which is Fs is whose information is known at time s. Okay? So this part again is taken out of the expectation. Okay? Then we have this part. Okay? We have this part. T minus Tm. So T minus Tm we can write as Wt minus Ws plus Ws minus Wtm. Right? And this part, Wt minus Ws, is future information, right? So it's independent of Fs. Okay? This part is independent of Fs. So its expectation is 0. Okay? And we left with the second term. Okay? So we left with the second term. All right? Okay. So this is just for the completeness of the proof. Okay. Intuitively, if you think, for the information up to S is known. All right? So whatever before S, you take out from the expectation. For any information beyond S is independent of Fs. And the expectation of the Brownian motion, the delta, right? The delta W, the change, its expectation is 0. Okay? So it's a martingale. Okay, now we want to prove the third property. Okay? So because we have shown that this integration is a martingale, the first equation in the third property is considered proved. Okay? So now let's look at the second one. Okay? We start from the expectation of this term. Okay? We start from the expectation of this term. When I is not equal to j. Okay? And for simplicity, we consider I is smaller than j. Okay? I is smaller than j. So we use the Tower property of expectation of x is the expectation of x given this f. Okay, we use this property. So this expectation we have, we just add one more expectation and condition on ftj. Okay, we condition on ftj. This is ti, this is tj. Okay, there may be ti plus 1. Okay, other points in between. Okay, but I time tj. Your delta wi, your cosine I, your cosine j are all known, right? The information are all known, right? The information of your cosine I is known at time ti, right? The information of cosine j is known at time tj. All right? So all this information are known, and so they are actually here, and because the information is known, so they can take out outside of the first expectation. Okay? And we left with the expectation of delta wj, which is independent of ftj. Right? Right? Because your delta wj is wj plus 1 minus wj. Right? Which is independent of ftj. So expectation is 0. Okay? So this expectation is 0. So the whole expectation is 0. Okay? So we show when I is not equal to j, this expectation is 0. And next, when we consider I equals to j, right? When I equals to j, you have your cosine I equals to your cosine j, okay? Delta wi equals to delta wj, right? So this will be expectation of cosine I squared delta wi squared, right? And this is expectation. We use the Tower property again. Right. And we know the information of cosine I is known at time ti. So it can be taken out from the expectation. So you end up with here. Okay? And again, because delta wi is independent of fti, right? So we can remove this one. And we left with expectation of delta wi squared. Right? And last week we showed for Wiener process, its variance is equals to the expectation of the square, because the expectation is 0, right? So the variance is equals to the expectation of square. And it equals to the duration, right? This is expectation of delta Wi squared. Okay? So this term will be expectation of Ti plus 1 minus Ti psi I squared. Right? And because Ti plus 1 minus Ti is determinate state, right? This is determinate state. It's not random at all. So you can just take out as from the expectation. So we show that the expectation of this the product of these 4 items is 0 if I is not equals to j. And if I equals to j, it equals to this one. Okay? The duration times the expectation of cosine squared. All right. Okay, next. Now let's consider this integration from 0 to t. And say, suppose t is between tm and tm plus 1. Okay? So, the integration by definition is sum of cosine okay, so I ignore the term for completeness first. Okay, I ignore the term for completeness first. So the square, the integration of this square will be the square of the sum, right? And this sum of the square of sum is basically right. So it says the square of 2 sum is just the sum of the product for each pair, right? The sum of product in each pair. Okay? So that's why the expectation of the square, we can write the expectation as a double sum. Okay? As a double sum. Okay? So let's ignore this part first. Ignore this part first for now, okay? For now. Those are for completeness. Let's look at the right part, okay? The right part. Okay, so for this right part, in the previous slides, we show that this expectation is either 0 when I is not equal to j, right? And so we only left with those terms that's I equals to j, right? So we only left with those I equals to j. And its value is this one, right? Its value is this one. Now what is this? This is the expectation of integration from 0 to t. This is the square of the process ds. Okay. Right. Right. This is xs squared ds. Right. So the proof is done. We show the variance or the expectation of the square is equals to the expectation of the integration of the square of this simple process with respect to t. Okay? All right? Clear? Okay. Now let's come back to look at these terms for completeness. Okay? So because each of the sum has a remaining term, right? That is t minus tm times cosine m. Right? So basically you have one additional term in each sum. So if you define this one, okay, look at this sum to be a, and this term to be b, then basically you have a plus b squared. And this is the a squared, right? Right? I define the sum to be a without any completeness term, right? Only the sum, the very nice sum to be a. And then the term for completeness to be b. So my integration is simply a plus b, right? My integration is simply a plus b, right? A plus b. So the a plus b to the square is a squared plus 2ab plus b squared, right? So my right part, the first equation is a squared. And this one is my b squared, right? And this is my 2ab. Okay? All right. Now, I want to show that this part, my 2ab here is 0, right? I want to show that. I want to show my b squared will goes to this part. And then my proof is complete. All right? Okay. So if we recall, if we know a and b are independent, right, then we know the expectation of the product is equals to the product of the expectation, right? And my cosine m is independent of delta w from t to t, from tm to t. Okay? Because my cosine m, the information is in ftm, and which is independent from the delta w beyond tm. Okay? All right? Okay? So we show that this expectation can be right. The expectation of square of the product can be right the product of each expectation. And the first expectation of square to be this is delta w squared, right? And we have used it many times that this is just delta t, right? This is just delta t. All right? So we have shown that this shows the b squared is what we want. Okay? This is my b squared. And this is my ab. Now this is my ab. Okay? So again, we separate what's independent, what's independent. Okay? Basically, you cut from Tm. Okay? You cut from Tm. And what's known up to Tm and what's not. And they are independent. Okay? And this is what is not known up to Tm. And this is what you already know up to Tm. And they are independent. And this expectation is 0. So I don't need to know about the others. Okay? So I proved that my AB is 0. So if we go back to this long equation, so we show that AB is 0, so 2AB is 0. Okay? So my B square is to be the completing terms. Okay? And this tells me this complete the proof. Okay? And this is a very important property. All right? Okay, the next property, the quadratic variation of this integration. Okay, the quadratic variation of this integration is also this one. Okay, the integration of the square of this simple process with respect to t. Okay, let's see. So to prove this one, first we have 0, which is t0, t1, t2, up to tn, which is t. Right? Now we take one time step, which is tj and tj plus 1. Okay, and we put it here. Tj and tj plus 1. Okay, and we put tj as s0. Okay, tj as s0. And then we further put another partition, s1, s2, all the way to, say, sk equals to tj plus 1. Okay. So then within this subperiod, okay, within this subperiod, my quadratic variation which is easy to compute because within this subperiod I have a constant psi. Okay? So within this subperiod, my psi is a constant. Okay? And because it's a constant, we can take out from the sum. All right? We can take out from the sum. And we know the quadratic variation of my WST. Okay, so this one I think we showed last week, right? This one, my delta W square goes to T, right? Remember last week we have this chart, right? When we have n to be a big number, my delta W square will be a straight line, right? And it's T. Okay? All right. So this one will goes to right? So the sum of my delta W square will go to the duration of this subperiod. Okay? So here I use the advantage that within this subperiod, I have a constant cosine. And then I can put up this subperiod into the whole time horizon. Okay? Now I come back to T0, T1, up to Tn equals to T. Okay? So within each period, my quadratic variation is this one. Right? And if we put it into a sum, sorry, here we should have a sum, right? Right. Oh, sorry, we don't have sum because this one within this okay, still within this subperiod, this quadratic variation equals to this one, and this one by definition is the integration with respect to dt for this subperiod. Okay, this integration is within this subperiod. Okay, and so we can expand this subperiod to the whole time horizon. Okay. So basically, we prove that this holds for every piece, or for every period of the simple process. We add them up together. All right. Okay, let's move on to some definitions. Okay. First, we define, okay, so we have complete the definition of Ito's integral of a simple process with respect to the Brownian motion. Okay? And we have shown what property this, okay, we define it this way, and it has property A, B, C, D, the linearity, okay? It's a martingale, isometry, okay? So we prove that. And now, we want to extend this integration from simple process to other process, okay? Okay. So first, we start from a definition of L2 space. So we define the L2 space to be all the FT adapted process such that its mean square is finite. Okay? The mean square is finite. Okay? This is my space. I define for any process, if first is FT adapted, second is this integration, expectation of this integration in the conventional calculus space is finite, then it's within this L2 space. Okay? And then we define another space D, which consists of all the simple process. And we will use a very important property saying that for any process in the L2 space, there exists a sequence of simple process, that such that the simple process will converge to the process in L2. Okay? For any process in the L2 space, I'll be able to find a sequence of simple process such that the simple process will converge to the L2 process. And this converge is mean square in terms of mean square, okay? The mean and the square. All right. So this is an illustration. We have Wt to be a Brownian motion. Okay? And now we see whether we can use a simple process to converge to this Brownian motion. Okay? So here n equals to 25, right? So, but if you have n to be a very large number, then you will see the two will converge. Okay? All right. So since for process in L2, we can find a sequence of simple process that converge to it, then we can define the integration of process in L2 as this limit, right? We have xn converge to x in L2, right? We have xn, a simple process that converge to x. And we know that my integration of the simple process with respect to the Brownian motion is well defined. All right? Then it is nature to extend this integration as to the process in L2, right? If xn converge to x, can we say this converge? And then we can use this integration of the simple process, right, as the value of my integration of process in L2. All right? So basically means can we define the integration of process in L2 as the limit of an integration of a simple process. Okay? But we have two things to clarify. Okay, we have two things to clarify. Number one is existence. Right? Number one is existence. Is this limit exist? Okay. So basically we want to define as the limit we want to define the integration of process in L2 as the limit of the integration of a simple process. But does this limit exist? And if it exists, is it unique? Right? Why unique? Uniqueness is important because you may have another simple process sequence, right? Right. And if this one, the limit is in, and this one, the limit is in, you want to make sure my integration will be unique, right? It cannot, if you have an option, you don't want your model to give you two price, right? Either this one or that one, right? Let's take a break. okay? And we'll show the proof. Let's come back at 8:20. All right. You don't need. I don't think you need a formula. You just need to understand what it means.
Or we have like we can bring an A4 paper and sheet.
It's go slow.
Okay. And do you have any practice problem? Because I don't know what kind of questions you ask.
I don't really have because last year I didn't teach this course.
Okay.
So I don't really have.
So about the quiz next week, it's all like we need to do something.
No, it's MCQ. This is a
multi-choice questions. So how's the rule like? So you have to.
Make announcement around the on the format. No, like on papers.
Sorry. Oh, okay. Maybe later. I just
Yeah, like the format and which cheat sheet allowed and what's allowed, what's not allowed, calculator allowed or not.
You don't need a calculator.
Yeah, I assume, but
Yeah. Sure. Later maybe.
yeah.
So we will need to choose all the just one.
It's very simple.
Okay, so I'm still a little bit confused about the LT part.
So L2 is the space of you consider it any process with finite like quadratic integration.
So and D is the set of all the simple processes, and it's like this means that we can simulate an LT functions with simple processes.
It means like because the simple process is a constant within a very short period.
Yeah.
And if this period is converged to zero, then which means for any process you can actually use a simple process to approximate. Right? And this is from practical perspective, you can use a simple process to approximate for example, and mathematically says you can always find a sequence. Not only you don't really need a sequence, you can always find exactly one simple process, right, that converge to this say linear process.
So it's really like what we have learned in calculus.
Yeah.
It's similar about the limits. It's called the limits.
This is just calculus. This is not a stochastic yet. This is just calculus.
Okay. So this is more like a concept.
Yeah.
It's just not like you need to calculate something.
It's a definition.
The definition.
Yeah. So basically we tell you this converge happens in this concept. The converge because you have a converge in because it's random variables. The converge can from different perspectives. Right? So this converge is like the expectation of this. The difference is mean square error. Right? This is like mean square error over from 0 to b. So this is 0.
And I'm still really understand one of the proofs here. I think it's behind the margin. Yeah,
tower property. This expectation is expectation of expectation. Right? We use the tower property. Okay, this is tower property. And because this one, and this one, they are all, their information are all known at time tj.
Because I is smaller than
Yeah,
J.
I is smaller than j. So at tj, all these three are deterministic.
Yeah.
So that's why you can take them out.
So they are constants.
Yeah, they can take out from the, because you
have
condition on your ftj, right?
Yeah.
So then, but then these two are independent. Right? This fj is here, and this delta, this fj is here, right? Right?
Yeah.
And this delta wj is from tj to tj plus 1, right?
Yeah.
So they are independent. So since they are independent, this conditional expectation is just expectation.
So we don't really need to care about this
Yeah,
part
this part
because
this is 0.
Yeah.
This is 0, so the whole thing is 0. Okay?
Okay.
Oh, no, we are not done yet, right? And this we use the same thing, exactly the same thing, right? Okay. The only difference is this is square, right? And this you need to move in to become a square. Again, these two are independent, and the expectation of this square is delta t, right? So now it's here.
So we are dealing with these two equations in a similar way, but
Yeah.
we need to move the delta wj into the
Yeah, because
expectation
now
it's
because
unknown.
because both are unknown.
Okay.
Yeah.
So the way to do it is to put the known parts here and put the
Okay, when you have a conditional on a filtration, right?
Yeah.
Whatever you know, you take out. Whatever you know, what you do not know, you put inside. At this tj, right? At time tj,
Yeah.
anything you know, you take out. Anything you don't know remains here.
Okay, I think I understand. Thank you.
Just to confirm, in this case, it can also be assumed that j is less than I, right?
Yeah.
So it's like a two-sided
Because
tennis.
okay, whatever whether I is greater than j or j greater than I, just like you just change this maybe to be ti, then delta wi. It's no difference.
And the rationale is basically because of the fact that filtration is we look at the history up to time t,
Yeah.
right? So anything after that is future, so we don't know.
No.
So it becomes like expected value is
Yes.
0. Okay, so that explains so basically we're using the idea that anything after the time j is a future value. That's why the expected value is 0, so you can take it out.
No. Okay.
Okay,
So what you take out from this expectation is what you already know,
right.
and then you left with the expectation of the future given the past.
Okay,
But for the Brownian motion, the beauty of it is that the future is independent of the past.
correct.
So
Okay,
that's why these two are independent.
okay.
So if you have expectation of A, condition on B, if A and B are independent, then this is just the expectation.
Okay.
So only when A and B are independent.
Okay.
Yeah.
So wait, in that case, sorry, which two terms did you say were independent?
Oh, when we learn the Brownian motion, right? So we have said this delta, they are independent.
Correct.
Right? So
Yeah.
basically, the future is independent. For Brownian motion, is the future is independent of past.
Past, correct.
So anything in the future is not irrelevant. Only now is relevant.
Okay.
Right?
Got it.
Yeah.
Which is why in this case the expected value tends to 0.
Yeah. The expectation of the future is 0.
Okay. Also, I wanted to confirm when you refer to completeness, what is the intuition behind it? Because you say do we add this term for completeness?
Okay. So the completeness is here. Here. So let's see. Here. Actually from here, right?
Okay.
Okay. Look. When I define integration as for each period as my cosine times my delta wj, right? But at the very last period, my t may not very nicely fall on tm or tm plus 1.
Okay.
So at the very end, I have a half period.
Okay.
So this is my half period.
Okay.
So when we prove for completeness means this is the major part.
Okay.
Right? Actually in the limit case, this is relatively like negligible.
Okay.
But when we have a rigorous mathematical proof, we want to make sure this whole thing stands.
Okay.
Yeah. So that's why when we prove this one, this is what we have in a very nice way. And then, but we have a half period here.
Okay.
So when the whole thing, we take a square, we end up with 3 items.
Okay.
And this is the A square, which is the nice part. And these are the items that to make our proof complete in a rigorous mathematical way.
So that's more to acknowledge that there might be like time that's not really definite, like not like a proper unit, right?
Yeah.
Okay, so it's more to acknowledge. Okay, so what you're saying is it's more to acknowledge like time periods that may not be a full unit of time.
So yeah, you have a t that is, because for simple process it's a constant within a period.
Okay.
But my t may not very nicely fall on the two ends, maybe in the middle.
Okay. Okay. All right. Okay. Thank you.
But that is only for the completeness of the proof. For you to better understand it's not really that important.
Is that similar to how there's a rest term in Ito's formula, like the original?
Oh no, it's not related to that.
It's not related to that. Thank you.
那就是我问一下，这个 quadratic variation 是根据这个 limit 来定义的一个东西。在这里我取这个 s i plus 1，就这样让 take limit，它确实是这样的。但是我们那个是一个 integration with respect to the simple process， 它也是根据这个 limit 来定义的。对，它现在外面还有个 limit， 那我们这样做现在是把两个 limit switch 一下。
也没有吧，就是你那是一样的 limit， 就是 time period 嘛。
time period。
对啊。
是一样的，因为我们是先有一个这个 integration， 然后再有一个这个 quadratic variation。
我们是 quadratic variation of the integration。And 这个 integration 呢，你要把它写成这个，就是我们的 definition simple process times 一个 delta wt 的形式。
对。所以我们现在说你要严谨的写出，全是我们有两个 summation， 两个 limit， 两个 limit 就是关于那个integration of。
那里面没有 limit， 里面没有
integration 它就是以 limit 定义的。
integrate OK， 你说 integration limit 定义是你的 conventional 的 calculus， 我们的 integration 的定义不是啊。
它不是，it's not limit。
它不是 limit， 我们的 不是这个。你看，我们没有 limit， 我们的 integration 没有 limit。
所以这个 limit， 那这就没问题了。这里说是 adaptive process， 它这个 x 它这个 simple process 是这样的。
它不一定是 xs 不一定是 simple process， 或者咱们的 xs 就很明显，它可以是 Brownian motion。
然后，那这个是这个
D 就是 any simple process。any
simple process， 这个也是，这个 space D 也是一个 simple。D
是 simple process，L2 不是。
L2 不是个 simple process。L2
不一定是 simple process。
不是
L2 是，比如说 Brownian motion 或者 linear process 就是一个 L2。它只要是符合这个，然后 FT adapted， 它就是一个 simple process。不对，它就是 L2 process。
好像就我们是用这个 simple process 来 approximate 一个。
对啊，其实它就是概念，就是说我有一个 process，比如说 unit process，然后我可以用一个 simple process 去 limit as a limit to。
因为我就像学数学时候定义的 power over the exponential， irrational exponential or rational number， 是根据 limit 来定义的。
差不多，就是这种。
然后这个东西就是他说，理论符号就是这个相当于这个，虽然是我们说定义，虽然说这个 x1 它虽然是a series of random number，a series of stochastic process。然后那这个它就是虽然它 stochastic process 也是个 random number，但是这个 limit 它指的是它是这个它的 limit 它具体什么意思？它是这个 limit。
哦，我们是想，
它是个很多 short convergence 来说 convergence equal。
我们想要的其实是这个 mean square convergence，就是这个嘛。
mean square convergence。
这种，就是我们之后要证它这个东西，你看是这个，那其实是想要证这种。something like that。我们等一下看 proof 你知道。
OK。我们现在这个 take integration 它只是对任意一个 random 因为这个 stochastic process taking 这个 stochastic integral， 它相当于是一个全是个 winner process take， 像你后面是个 winner process。
就是一个 winner process。
对，后面可以是别的一个 random 一个 stochastic process， 不是 winner process， 这可以。
然后如果你们去学那个有一门课好像叫 directive pricing， 比如说这个 market 上会有一个 model 叫 jump diffusion model， 那你的这个 process 就是一个跑送 process。
对，我也在上面，应该还没教到。
不知道他会不会教了，因为我也没上过那门课。我没教过那门课，所以不知道。感觉看这个名字应该会教，但具体会不会教就不知道了。但是 jump diffusion 是一个比较 popular 的 model。
OK。关于这些有没有什么书可以为他们做？
就你看第一节课那有 list 的那个
最贵。OK， 我是。
就是这部分这个到底有什么？
就是这个 definition 那个 progressive variation 嘛，这个I 是 integration， 这个是变成了 TI integration， 就是这个嘛，就是两个，就是它的 square 嘛，就是这个东西没什么用，这个是打基础，就是具体后边你要说以后我能不能用它来做什么，这个在 in practical 是用不上什么这个东西，这个是用来打基础，就是我不可能我上来就丢给你，告诉你就算就行，那哪些东西能这么算，哪些东西不能算，为什么可以这么算？就好像我们学什么东西都得从一点一点来嘛，这样。你要说它有什么用，其实。不做 research 其实感觉用不上它做什么用。
我的问题就是 x square 的平，就比如说 xs square， 它到底就是放在 model 里面，它等于是个什么概念？
就是一个 square 嘛，就是如果它是5的平方就是10，不是它25啊。
那它在 process 里面到底？
也是它的 square 啊，你知道，它是一个 function，process 就好像 你这个 simple process，比如它等于 cos i， 那 cos i 的 square，x square 就是 cos i 的 square， 如果它是5，那它平方就是25嘛。等你们学到一周四安嘛，然后看那个那个 dn square， 就能看出来它是有意义的，就是它的一个 second order term。你就把它当成一个数就可以了，其实。
OK， 好，好，谢谢。
Okay, let's continue, okay? Let's continue. Okay, now we want to prove that the integration for process in L2 as the limit of an integration of a simple process. Okay, we want to prove this limit exists and is unique. Okay. Okay. Now, first, we will show that this sequence of simple process forms a Cauchy sequence. A Cauchy sequence means, so if you have a Cauchy sequence in and say im, and then basically says for given a very small epsilon, you can always find n and n such that their difference, okay, their cubic difference can be smaller than this epsilon. Means they can be arbitrarily close. Okay? So if we can show that it forms a Cauchy sequence in this way, the expectation of the mean square difference, the mean square difference converges to 0, then we can use a very good property of a Cauchy sequence saying that it will converge to something. Okay? Okay? We are not saying it converges to what, sorry. We are not saying what it converges to. We just say if we can show it's a Cauchy sequence, then we know it converges to something. Okay? And then we can say there exists, because it converges to something, then there must exist a random variable it, right? Such that this equation, this mean square difference, it converges to 0. Okay? So by doing so, we prove the existence of a such limit. All right? Okay, so we want to show if we have in and m converge to a process in L2, then its mean square will converge to 0. Okay? So by definition, in and im are integration with respect, are integration of simple process with respect to Brownian motion, which we have defined in the first half of this lecture, right? So, and by linearity, we can write it in this way, right? Right? It's basically the difference of two integration of simple process. Right? And by Ito's isometry, this mean square is the variance, right? This is the variance. All right? And again, this is also the integration of the square with respect to t. Okay? If you go back to our slides, there is a label for equation 3, right? We proved this one. Okay? the conversion between the integration with respect to a Brownian motion and the integration with respect to t. Okay. All right. So now the problem becomes in the conventional calculus space. Now its integration is respect to t. Now we're going to use the fact. Okay, use this fact. A squared plus 2ab plus b squared. Okay, a plus b squared is smaller or less than 2a squared plus 2b squared. That is because a minus b squared is greater than 0. All right? This is very straightforward. Okay. Now, let's look at this square within the expectation and the integration. Okay? This square. So we'll break this two simple process, and in middle, add in xs. Okay? Add in xs, which is the process that xn and xm both converge to. All right? And by this inequality, we can break these two into these two parts. All right? Okay. And then we say if xs is a process in L2, then xn and xm will converge to xs in a way that such expectation is 0. Right? This is by definition. So then we prove this is 0. Okay? All right? So remember, we want to show this in and m converge. Right? And now we saw it's 0. So we show that the in, this sequence of simple process is a Cauchy sequence. All right? So we prove the limit exists, right? Because Cauchy sequence converge. Okay, so there is a limit, a random variable it, such that the int converge to it. All right? Okay? Okay, now we want to show that this converge will converge to the same thing. Okay? Every simple process that converge to the process in L2, the integration will converge to the same thing. Okay? So suppose we'll say we have two simple processes, okay? xsn and xs tilde n. And both converge to xs. Okay? Both converge to xs. All right? And we define int and in tilde t to be the respective integration of simple process with respect to Wiener process. Okay? And then we know that int will converge to both int will converge to it, and in tilde t will converge to I tilde t. Okay? Because there is a Cauchy sequence and there exists a random variable, right? Now it becomes it and I tilde t, respective. There exists respective random variable as the limit. Okay? So now we know we have int converge to it, in tilde t converge to I tilde t. And we want to show I tilde t converge to it. Okay? So let's just put up the structure here, okay? What I want to show is I tilde t converge to it. Right? This is what I want to show. What I know is I tilde t converge to in tilde t. I tilde t converge to, sorry, it converge to int. Right? And my int, by definition, is my xsn dws. Right? And my int, sorry, this is tilde, and this is xsn. Right? This is definition. And further, I know my xs, okay, my xsn tilde and my xsn both converge to xs. Okay? Right? If we do not want to know the details of the rigorous mathematical proof, this looks already converged. Right? So every line in this circle, they are either converged or equals to by definition. Right? Okay? Okay, so let's look at the details. Okay, so we know xs and xs tilde, they are simple process. Okay, xsn and xsn tilde, they are simple process. So the difference is still a simple process, right? And then we have shown that for the Edos integral, okay, so this difference is still an Edos integral, right? Right, it basically is x s tilde n minus xsn. Right? So this is still an integration of Edos integral. Right? Right? And we can transform this integration with respect to Brownian motion to t. Right? Okay? This is the property we show for the integration of simple process. Okay? All right. And now, we use the same property just now, that a plus b squared is small or equals to 2a squared plus 2b squared, right? We write x as tilde n minus xs plus xs minus xsn, right? We write this difference to 4 terms, right? We break them to an xs in between. And by definition, this and this both goes to 0, right? That's how it converge, right? That's how they are converged. Right? we have xn converge to x, xn tilde converge to x. How the converge defined is defined this way, right? It's defined this way. So they are 0. So now we show xn tilde converge to xn. Okay? Now we go back this. These two converge, right? Sorry. Right? Previously, let's look at this circle again, okay? Previously, the link between in tilde and in is true the definition with respect to the respective simple process that converge to the same xs in L2. Right? Now we prove directly that now xn and xn tilde, they converge to each other. Right? Okay? Okay. Okay, so basically we say this converge will lead to the converge between xn and xn tilde. That's what we have just done. All right? Okay. Next, we'll use another algebra property. A plus b plus c squared is smaller than 3 times a squared plus b squared plus c squared. Okay? Okay. Now, you want to close the gap, showing that I tilde close to I. Oh, sorry, converge to I. Right? That is what we want to show. The both will converge to the same thing. Okay? Basically, we are proving it and I tilde t, they are the same thing. Therefore, the two simple process, the integration of two simple process converge to the same thing. Okay? Now, we break this difference, now not 2 parts, but 3 parts. Okay? I tilde and I tilde n. I tilde n and in and I. Okay? Remember what we proved in the last slides? In tilde and in, right? So in tilde and in, this is 0. Right? And these two are 0 because by definition, right? Right. This okay, the I tilde converge to in tilde, in converge to I is what we show when we prove the existence. Okay? If you go back to our proof of existence, you want to prove this one, right? Okay? See? Right? Equation 9. So using equation 9, we show the first item and the last item of the last equation. The last item goes to 0. Okay. All right. And this complete the proof. Right. So this proof is only help you to better understand the idea. Okay. So if you find it a little bit difficult to digest, try to just understand this circle, okay? Try to just understand this circle, okay? How the converge happens, all right? Okay? Okay, now we can formally define what is stochastic integral or what is Ito's integral. So a stochastic integral in L2 is just defined as the limit of the simple process, the integration of a simple process with respect to the Brownian motion. Okay? And this converge, or this limit, is in the sense of mean square. Okay? Mean square. Expectation, the difference, the square. Okay? All right, so that's the major part we have achieved today to formally define, or well define, what is a stochastic integral. Okay. This is an approximation of the Ito's integral. Okay? So we have WT and WTN. Okay? So this WTN is to approximate WT. And then we have the two integrals. Okay? We have the two integrals on the right. On the right. Okay? Then you see the blue one and the red one are pretty close when you only have n equals to 25. Okay? So if you are interested, maybe you can write a simple Python code and increase n maybe to 10,000, 100,000, 1 million. You will see the one on the right basically is the difference will become invisible. All right? Okay. So basically, most of the properties that applies to the integration of simple process can be extended to the integration of L2 process. Okay. Okay, so let's see. The first one says this integration, this Ito's integration is adapted to past history. So it's FT adapted. Okay. We know XT is FT adapted, right? So if XS you integrate of a process with respect to the sorry, I shouldn't write XT to confuse you. WT. WT is FT adapted. Okay, excuse me. So we know WT is FT adapted. So the integration with respect to WT is also FT adapted. Okay? And this integration is continuous with respect to T. Okay? It's continuous with respect to T. And the second one, third one are inherited from the integration of simple process, right? The linearity, the martingale. They are the same as the simple process integration. And also the fourth one and the fifth one, they are all the same as what we learned in the simple process integration, right? Okay? So they're not new. Just like because we defined it this way, so the properties of the integration of simple process can be extended to the integration of L2 process. All right? And there's a corollary, okay? So suppose X is integrable in terms of the conventional calculus space, and is life continuous, and is adapted, or FT adapted. Okay, it means okay, XT is FT adapted. Then this integration can be defined as the limit of this one. Right. Intuitively, if you think, when my norm goes to 0, okay, when my norm goes to 0, my delta t goes to 0, right? For each period, it goes to 0. And then for each period, because the duration goes to 0, then my L2 process XS will become a simple process, right? Consider a Wiener process. Then your delta t is small enough. If your delta t is small enough, then your Wiener process will be like a simple process, right? As long as your delta t is small enough. Okay? So this proof is relatively simple, just skip it. And let's look at some examples. Okay, let's look at some examples. So the first one, the integration of Ws dws. Okay. First, we want to see whether it's well defined. Basically, we want to know whether Wt or Wiener process is in L2, right? Okay. Is it in L2? We want to know this one. Right? We want to know this one. And then by Fubini's theorem, because expectation is just another integration, right? Your expectation is just another integration. So you can switch the two integrations and then put the expectation of the integration of the expectation inside. That's why you see that these two integrations actually swapped. Okay? All right. And now, this one, the expectation of Ws squared. We saw it so many times. It's just the variance, which is S. Right? So integration of S ds, this is the first integration you'll learn in calculus, right? It's half S squared. So this one is finite. So we show that Wt, or the Wiener process, is in L2. Okay? Since it's in L2, it is well defined in the Ito's integral, right? Now, let's consider a partition from 0 to t and define the sequence of the simple process as eta tn. Okay, this is the sequence of the simple process that converge to the Wiener process. Okay, so the simple process equals to the Wiener process at the beginning of each period. Okay, this is important. It ensures that they are Ft adapted. Okay, all right. And then you want to compute the limit of the integration of this simple process. Okay? Remember, we define this simple process as the value at the beginning of the period, right? Of the Wiener process, right? If you recall this definition, it equals to the value at the beginning. Okay? Sorry. Okay? And now we want to find this one, right? By definition. And by algebra, we have WTJ times WTJ plus 1 minus WTJ is equals to WTJ plus 1 square minus WTJ square minus WTJ plus 1 minus WTJ square. Okay, you can verify this. Okay, you can verify this. This is simple algebra. Okay, this is simple algebra. So this sum, okay, sorry, this is 2. I forgot the 2. Okay, will be the difference of these two sums. Okay, this is simple algebra. And next, the first sum are just like if I believe you saw this sequence in algebra, right? You want to calculate 100 minus 99 plus 99 plus minus 98 plus 98 minus 97 plus 97 minus 96, right? This is similar. And then you will left with only two terms, the beginning and the last, right? You only left with beginning term and the last term. That is WT squared minus W0 squared, right? And we know W0 is 0, okay? So that's why the first sum will only be the WT squared. How about the second sum? How about the second sum? The second sum goes to the second sum is t, right? The second sum is t. Right? So this is just t. So we show that this integration is half WT squared minus half t. All right? Recall, if you have from 0 to t x dx, this will be half x squared from 0 to t, right? And this is half t squared, right? This is conventional calculus, the easiest one, right? And now, if you have ws ds integration, you will have half wt squared. That, okay? Without the minus half t is conventional calculus, right? And this additional half t is a correction term. Okay? This is the correction term. And you will see it when we introduce the Ito's formula. All right? Okay, second one. Second one. You want to show that the integration of a constant s, the integration of t, s is the time, right? dws is equals to t times wt minus the integration of the Brownian motion with respect to time. All right. Okay, let's start from definition. The integration of s with respect to the Wiener process can be write as this sum, right? So if you look carefully, actually write the sum should from I equals 0 to n minus 1, but for convenience, I just add n, right? Anyway, you will have n goes to infinity, right? So if you want to have rigorous mathematical proof, you should write n minus 1, but it doesn't really matter here. Okay. And now, this is the beginning term, right? This is the original term. Then we add something to break them, right? So we have used this technique many times to prove what we want, right? Okay, you should be familiar with this now. So the first part, the first two items have a common WT, right? Have a common WT. And the second two terms becomes consecutive, right? Becomes what we see just now, 100 minus 99 plus 99 minus 98, okay? Okay. So the first one, the first sum, by definition, is the integration with respect to t, right? Right? This is dt, right? So first is, by definition, is the integration with respect to t. And then the second one becomes twt minus 0w0, right? All other items in between are cancel each other. Okay, so prove that. Okay, last exercise. We want to show the integration of Wt squared, okay, with respect to dt. Okay, and we will use the two hints here. The first hint is easy, it's just an algebra. It's easy to understand, but I guess it's pretty difficult to come up with it when you really need to use it to prove, right? Okay, but try, as long as you understand it, it's okay, okay? You can verify this algebra holds, this equation holds. For the second one, it says this whole items converge to 0 in L2. How do we verify that? How do we verify that? You verify that by expectation of this guy is 0. And the variance of this guy goes to 0. Okay? You can try that after class. So now we'll just use this hint. Okay? Okay. We start from what we want to calculate, the integration of w squared with respect to w. Okay? And by definition, it is the sum of w squared times dw, delta w. Okay? And then we use the hint of algebra, the first hint about the algebra, to break them into 3 components. Okay? 3 components. Okay? The first component, again, becomes left with only the first and last item, right? Everything in middle are cancelled. That's the first component. For the second component, we'll use the hint. This one will converge to this one, right? We use, this is derived from the hint, from this one, okay? From the second hint, okay? This is from the second hint. All right. And the last one, do you see what is the last one? That is the third order variation of WT, right? Remember what is the first variation of WT? Infinite. The second variation, T, right? And in one of the exercises we show if you have P's variation is finite and you have a P prime which is greater than P, then the P prime order variation is 0, right? Remember that exercise? Okay, and then in that exercise we highlight because the second order variation is T, the third order variation is 0. Okay, so it's all connected. This is 0. All right. And then the second item, by definition, this one, by definition, it will be just the integration of WT dt. Okay, and that completes the proof. Okay, so that's all. Today we first introduced stochastic integral with respect for a simple process, okay? And then we extend to process in L2. And we prove this integration or this limit exists and is unique. And then remember the shared properties of this integration, linearity, martingale, and extra, okay? And then we did a few exercises. And then next week, we'll have our first quiz, okay? I think I mentioned in the first lecture, the quiz will be in MCQ format, okay? For each question, you will have options A, B, C, D, E, F, G. Just kidding. A, B, C, D, E, I think maximum is E. I don't have F. I don't think I have F. All right, most are ABCD, okay? Most are ABCD. And there are only 5 questions, okay? Only 5 MCQ. So if you have a good understanding of the lecture notes, you should be able to finish it about 5 to 10 minutes, okay? Yeah, basically if you remember what is in the lecture notes, you can finish in 5 to 10 minutes, okay? But I think I'll give you either 20 or 30 minutes. Okay, depends on how we're gonna do in the next week. Okay, if we finish around 9, then I can give you 30 minutes. Okay, and then it's closed book. Okay, it's closed book. All right. You don't really need a calculator at all. You don't need calculators, okay? You see our exercise, your calculator won't help, okay? And any other questions about the quiz? No, it's closed book. Okay, it's closed book. The concept is only up to today, okay? Only up to lecture 4, okay? Yeah, so it's only up to today. You get what? It will. You can just write it. Yeah, it'll be human marked. So don't worry. Yeah, it'll be human marked. Handwriting. I'll give you the quiz paper after next lecture. Then you have 30 minutes to complete here. And then you submit and you can go. Okay, it's not online, it's not online. And if anyone cannot make it for the Monday quiz and you want to attend for Friday, you must let me know in advance. Okay? But don't worry, you got different question sets. Okay, you got different question sets. Okay? So, any other questions about the quiz or anything? I think it's depends on when I can finish the lecture, either 4 to 4:30 or roughly the same time. The lecture Monday is 7 to 9 normally, or 9. Then Friday is 2 to 4. So roughly the same time. Yeah. At the end of the lecture. Okay. If you don't have any question, then you're free to go. Thank you. Hey, hello.
To prove for the quiz?
No, it's MCQ. You don't need to prove anything.
Because you know, talk about
This is not proof. This is calculation. Okay. This is calculation. This is called calculation.
Okay.
This is called proof.
Can you bring flex paper, please?
Honestly, you don't need one. Okay. I don't think you need. Yeah.
I want to apply to attend the Friday ones.
Can you write me an email with your name? Yeah.
Similar to the exercise, like groupings or.
I only got one or two questions similar to the exercise. Yeah. And they are easier. They're much easier than the exercise. Then the remaining is just concept. Whether you understand the concept.
Okay.
Yeah.
Thank you. Yes, no problem.